Okay, so next up we have a rather short lesson that's just going to be a couple of corollaries of Tutte's theorem on perfect matchings. Maybe I'd better just go back and sort of remind you what those are. Both of these corollaries are fairly simple theorems. They're not, I guess they're not especially hard to prove, but they're both fairly meaningful. The first is going to have a kind of an important take-home message with it as well. Maybe the thing I want to just sort of impress upon you is that Tutte's perfect matching theorem, it sounds like the end of everything. You know exactly when a graph has a perfect matching, but in fact it's the beginning of a much bigger story. So there's much more that we'd like to understand about perfect matchings and many kind of fascinating unsolved problems, and anyway, it's a very active area still. Okay, so let me return to Tutte's theorem and remind you how this works. So, part of the genius of Tutte was to find this incredibly flexible and wide, the sort of applicable obstruction. So this nice reason a graph doesn't have a perfect matching. And here's the thing Tutte found. So suppose your graph contains a subset of vertices X, and when you delete that set of vertices, you see lots of odd components. So what I'm drawing here, I'm just going to call them G1 and G2 on down to, say, G sub T. And maybe there could be some even components out here. I don't care. So what Tutte observed is, again, if you have a set of X of vertices with the feature that the number of odd components of G minus X, if that is larger than the size of X, then there is no perfect matching. Again, this is fairly easy to see. If you were to suppose that you have a perfect matching, look at each of these G sub I sets. Each G sub I, it's a set of vertices of odd size. If you want to have a perfect matching and you're staring at a set of vertices of odd size, you better at least once have an edge that has one end in that set and one end outside, right? So for each of these GIs, if you're hoping to have a perfect matching, you're going to have an edge of that perfect matching with one end in the GI and one end outside. Well, where can that other end be? Well, GI is a component after you delete the set of vertices X. So that means the only edges in the graph that have one end in GI and the other end outside, well, they have their other endpoint in X, right? So if you're hoping to have a perfect matching, then for each of these G sub I components, you're going to need an edge that has, your perfect matching is going to have to use at least one edge that has one end in that G sub I component and one end in the set X. And now we've got a pigeonhole problem. If there are more of those odd components than there are vertices in X, then you're not going to be able to make a perfect matching here, because you're gonna have, I mean, your perfect matching, by what we've said, you're gonna have to pick up two edges that have ends in different G sub I components and join to the same vertex in X, but that's no longer a perfect matching. So this is an obstruction to the presence of a perfect matching, and the remarkable theorem Tutte proved is that is the end of the story. If you have a graph and either it's going to satisfy this condition there because it's going to be a subset of vertices X that gives you this obvious obstruction, or if none of those obstructions are present, then you are guaranteed to have a perfect matching. It's a beautiful theorem. Now, you might be interested though, so I mean, we're graph theorists, we want to understand matchings in graphs, so I give you a graph that doesn't have a perfect matching. Well, Tutte says we'll have a set like this, but well, how close can we get? Can you find a matching covering all but two vertices, or all but three vertices, or all but four? How close can you get to a perfect matching, right? This answer is very nice if your exact question is, do I have a perfect matching? But what if I'd just like to know how big of a matching can I find? And it sounds like, well, I mean, that's a much bigger problem. Now I'm doing some optimization and there's a lot more to consider. But it's going to turn out that the answer is really encapsulated in Tutte's ideas still. So let's see why. So, okay, so let's maybe just to be very concrete here. Suppose I told you that not only the number of odd components of g delete x bigger than the size of x. Maybe I'll tell you this is equal to the size of x plus 6. Okay. So let's suppose we found a set x for which not only do I have this inequality, the odd components are bigger than the size of x. Sorry, the odd components of g delete x is larger than the size of x. Maybe I found one where it's bigger by 6. So in this case, I claim that any matching in the graph is going to have to miss at least 6 vertices. So for any matching you choose, there will be at least 6 vertices in the graph that are not incident with any edge of that matching. And this really, this is just the same argument, the same pigeonhole principle. So what's going on now, again, I'm not saying perfect matching anymore. So I'll have to be a little bit careful in the way that I say things. But if you choose a matching here, remember now you've got 6 more things here than you have over in X, right? Now let's choose a matching. Well, for each of my g sub I components, one of two things is true. For each of those g sub I components, either your matching is going to have to use some edge with one end in that g sub I and one end in X, or your matching is going to have to miss at least one vertex in g sub I. Right, so for each of those g sub I components, here I have I runs from 1 up to t. So I've got t of these components there. For each of those t components, either the matching that you're showing me now, I'm arguing that every matching is going to miss at least k vertices, or sorry, at least 6 vertices. So you're giving me a matching. I'm going to look at each of these components from g1 up to g sub t. For each of these components, either your matching is going to have to miss a vertex in that g sub I, or your matching is going to have to use an edge with one end in that g sub I and the other end in X. Now, if I've got 6 more of these g sub i's, then I have vertices in X, then at least 6 times you're going to have to miss one of those vertices in g sub I, and that means that your matching is going to, the best it can do is cover all but 6 vertices. So if the number of odd components of g delete x is equal to the size of x plus 6, we can actually see it's really stronger. Not only does your graph not have a perfect matching, but in fact, for any matching that you choose, that matching is going to not be incident with at least 6 vertices. So we're seeing that this obstruction that we found before actually has some forcing even kind of further down the line. If you can find a set X where the number of odd components of g delete x is much larger than the size of X, then not only is it saying you don't have a perfect matching, but it's saying you aren't even very close. And this is an observation due to, okay. This is an observation due to Berge, and let me state this theorem. So actually, I stated it a little bit differently than I did in the notes. What I'm interested in doing here is I want to talk about the fewest vertices not covered by a matching, and I'll just say it this way. So let's let k equal the maximum over all subsets of vertices of G of the number of odd components of G minus X minus the size of X. Now, let me note, you're always allowed to feed in the empty set. So you're allowed to take X equal to the empty set. If you do, this is going to be the number of odd components of G minus 0. So this parameter K is always going to be greater than or equal to 0. So K is a non-negative parameter. What we know is if K is 0, then that means the number of odd components is always less than or equal to the size of X. And that means that your graph does have a perfect matching. That's Tutte's theorem. So when this K is equal to 0, you do have a perfect matching. Berge took Tutte's theorem and kind of bootstrapped it. And what he proved is the following. So if K is this parameter, then the largest matching in G covers all but K vertices. Right. So, and we've already seen one kind of one side of this. We've argued that if this parameter is equal to K, this is what we had before on the previous page. If this K was equal to 6, you found some set of vertices X where the number of odd components of G delete X is 6 more than the cardinality of X. If that's what you saw, well, then every matching is going to have to miss at least 6 vertices. So you're going to be off by at least 6. And so if we take K to be the maximum of this, well, then we can see, this is the same argument that we saw before, the size of the largest matching, you're going to have to miss at least K. So the proof here is, and I'm just going to sort of reference our observation. So by our observation, every matching is going to miss at least K vertices. So what I need to prove to you is that there is a matching that covers all but K vertices. So to prove is that there is a matching covering all but K. So if we can do that, then we will hit our target here. And now's maybe where the main take-home message from this whole batch of notes is kind of lying, or this sort of little segment I'm doing right now is lying. The thing we're interested in doing is showing that our graph G has a very big matching. Now, we are very good at checking if some graph has a perfect matching. We have a very similar problem. I'm now trying to prove that our graph G, well, doesn't have a perfect matching, but has one that's pretty close. It's supposed to have a matching that covers all but K vertices. I am going to do that, following Tutte here, by the following method. I'm going to take this graph that I have and this similar sounding problem. I want this matching that covers almost all the vertices. And what I'm going to do is I'm going to make an auxiliary graph. We're going to make a new graph. I'll call it G+. And the new graph is going to have the property that if the new graph has a perfect matching, then our original graph G has a matching covering all but K vertices. So what we're going to do, and in fact, it's going to be if and only if. So what we're going to do is we're going to transform our problem by making a new graph, right? Again, I mean, this is a thing mathematicians just love to do, right? So we have a problem that we've solved. We are good at finding perfect matchings. We know when a graph has a perfect matching. Well, if you give me a graph and you're asking me some problem about finding a big matching, if I can take that and encode it as a problem about finding a perfect matching in some other graph, well, then I'm going to win, right? Because I'm good at that perfect matching problem, and I'll be able to deduce the original. So the key idea here is using an auxiliary graph. We are going to take our problem about finding a large matching, and we're going to encode it. We're going to find an equivalent problem that is about finding perfect matchings in some larger graph, in some auxiliary graph. And again, since we can do perfect matchings, we will then apply our theorem over there, and when we get our answer there, it's going to translate back to the answer that we want. So I want to prove there's a matching covering all but K vertices. Here's going to be the idea. So I'm going to extend G to a graph G+, and here's the idea. I want my original graph G to have a matching covering all but K vertices. So if I look at that best possible matching, there are going to be K vertices left out. Well, I want to turn this into a perfect matching problem. These guys can't match to anybody over here. Let's match them up to some new vertices. what we're going to do is I'm going to make a set of k vertices that I add to my graph, and I'm going to join those k to everything. You know, of course, I don't know which ones these are in advance, right? So what we're going to do is we're just going to take a set of k vertices and make those vertices adjacent to everything in the graph. So I'm going to extend G to a graph G plus by adding a set, I'll call it Z, of k vertices, each of which is adjacent to every other vertex in the graph. Right? So in terms of the picture here, so here's my original graph G. I'm adding a new set Z of k vertices, but I've got all these edges in here, and I in fact have all the edges in Z, although I'm not going to draw it just because it's going to mess up the picture. But now let's take a look. Suppose I told you that this graph G plus has a perfect matching. That's great news. Just delete from that perfect matching all those edges that use a vertex in Z. You're going to be removing at most k edges from that perfect matching. What's going to be left is a matching that's a matching in the original graph G, and it's got to cover all but at most k vertices. So if G plus has a perfect matching, then I win. So if G plus has, oh, I've switched colors. Not that that matters so much, but. So if G plus has a perfect matching, then we're going to win. Then we'll just take that perfect matching. Again, we'll delete from that perfect matching any edge incident with a vertex in Z. That means we're going to be deleting at most k edges from that perfect matching. And each time we delete an edge, we're removing at most one. We're leaving at most one vertex from the original graph G uncovered by our matching. So we'll do that at most k times, and that means we'll be finding a matching in the original graph that that indeed covers all but at most k vertices. So that's good. So that's, I mean, in fact, that's great. And now we're really zooming here. So now we've turned our problem into a problem about finding a perfect matching, and we're very good at that. Now we're going to apply what we know about perfect matchings. Now, before I do that, I need to make a quick observation about parity. If the original graph G has an even number of vertices, then, or actually, maybe let me write down my claim here. My claim is that the number of vertices of G plus is even. Or another way of saying that is the number of vertices of G, it has the same parity as K. I'll just write same pair as K. So let's just think through that. Again, this is a thing we saw before when we were doing Tutte's theorem. Parity is super important here. I mean, you see we're saying even and odd all over the place. If the original graph G has an even number of vertices, then for any set of vertices X that you delete, the number of odd components and the size of X itself will be, they're either both even or they're both odd, right? Because if I have an even number of vertices in the original graph, well, after you delete X, suppose X has an odd number of vertices. When you remove it, you're going to have an odd number of vertices in the graph, and that means you'll have an odd number of components of odd size. Conversely, if my original graph is even and I delete a set of even size, then I now have an even graph, and that means you'll have an even number of vertices, of components of odd size. And the argument just flips. If the original graph has an odd number of vertices, then when you delete from it an odd number of vertices, you're now going to have an even number of odd components. And if you have an odd size vertex set and you delete an odd size set, then you'll be left with an even number of odd size components. So this is all to say that, I mean, we can just check all these parity things that I may have said that a little bit quickly, but at the end of the day, that parameter k that we're getting, which is this maximum of odd g delete x, excuse me, it's the maximum of the number of odd components of g delete x minus the size of x. That parameter itself, this, sorry, let me just draw it here. This guy here itself, this guy always has the same parity as the number of vertices in the original graph. So if the number of vertices in the original graph is even, that number is always even. If the number of vertices in the graph is odd, that number is always odd. Now, we've taken k to be the maximum that we can see there. We're then going to make a graph by adding k vertices to our original graph. Well, if we had a graph with an even number of vertices, then we're going to add an even number. If we had an odd, then we're going to add an odd. And this means that we're going to have an odd, sorry, that means that when I look at the number of vertices in G+, that's always going to be an even number. So at least G+ has a chance of having a perfect matching. So now let's, I'm going to wave my hands a little bit. As usual, there's more detail in the notes, but let's think about the graph G+ and imagine now we just have to prove that G+ has a perfect matching. So we want to prove that however you delete a subset of vertices, the number of odd components that you see is going to be less than or equal to the number of vertices you delete. Now, because we checked that we're okay on parity, we know we're safe on the empty set. If you delete the empty set, then the number, well, sorry, what am I saying? No, sorry. Let me take that back. What I was saying was irrelevant. I mean, we know we have an even number of vertices, so we at least have a chance. Now, let's imagine deleting a subset of vertices and asking what we see. If you suppose we, well, I should say, I'm safe to assume here that k is bigger than 0. We know that if k is equal to 0, you know, if k was equal to 0, then your graph has a perfect matching. That's already Tutte's theorem. So I can assume here that k is positive. So there's some subset of vertices that you can delete that gives you more odd components. Now, if you do not delete any vertices, so which is to say which means we've added at least one vertex to our graph here. Right, our set Z is going to have positive size. This k is positive, so we're adding some vertices to our graph. Now, let's think about this graph. If you leave, so let's imagine deleting from this graph G+ a set of vertices x. If your set of vertices x does not contain all the vertices in Z, when you delete them, you're still going to have a connected graph. Right? If when you delete from this graph some set of vertices and you leave some vertex in Z still there, that vertex just individually joins to every other vertex in the graph. So your graph is still going to be connected. So that means that our only hope here of having the number of odd components be 1 or be larger than 1, we have to delete all the vertices in Z. The only sets I need to worry about are subsets of vertices X that include everything in that set Z. But now this is just our parameters lining up. So now if you take a set of vertices X that contains every vertex in Z, well then you're going to have to contain, you contain k extra vertices. And now we're just back to this, now we're back to this feature. So in other words, your set of vertices, so I'm going to operate in the graph G+ now, and I'm deleting a set of vertices X and asking about the odd components. Sorry, I don't have much room here, but I'm deleting a set of vertices X and asking about the odd components. Your set of vertices X, it's got to contain all of Z. So it really contains some subset of vertices X prime from the original graph plus all of Z plus k more. But I know that, but now what's happening is these odd components over here, these are exactly the odd components of the original graph that you get when you delete not the set of vertices X including Z, but X without Z. So in other words, well, this is written better in the notes, but G+ does have a perfect matching. So the number of, what I want to say is g plus minus x is connected unless z is a subset of x. And this means that our only hope to not have a perfect matching in G plus is if the set X of vertices that we delete contains all of Z. And that means that this set of vertices X is going to consist of all of Z plus some set X prime, X without Z. But that set X prime, that's just a subset of vertices of our original graph. And when we delete it, we're seeing exactly the same odd components. Because for every set of vertices X prime from the original graph, when you delete X prime from the graph, the number of odd components that you see is going to be at most K more than the size of X prime itself. That's going to imply that G plus satisfies this formula. So I didn't have a lot of room to write things here, but the details here are not all that exciting. I mean, there's just a little bit of bookkeeping. So again, the key point here is that what we've done is we've taken our original graph G. We're trying to prove that G has a very large matching, a matching covering all but K vertices. We've encoded that problem as a problem about some larger graph G plus having a perfect matching. We've done it in a pretty simple way by adding K vertices to our graph that are joined to everything. We now have this nice feature that, well, if this new graph G plus we've just made has a perfect matching, we chuck the edges that touch one of the newly added vertices and we get the matching that we want in the original. And now we can apply Tutte's theorem. And again, because when we added these K new vertices, we joined them everywhere, if you're hoping to delete some set of vertices from this new graph and have a lot of odd components, you have to delete all K of those newly added vertices. So if in our original graph, K was the maximum of this parameter, K is the maximum of number of odd components of G delete X minus the size of X. Now we've added K new vertices. If you're hoping to find a set that's going to be an obstruction for a perfect matching in G+, you're going to have to use all K of those newly added vertices in your set X. But then that's just padding your set X with K more than we had before, and K is exactly the extreme value here. So that K extra of padding that you get, that guarantees that G plus is going to have a perfect matching and gives the matching in G. So yeah, I'm sorry I wasn't sort of able to write more, but the proof is there. And really the main thing from my standpoint is this kind of take-home message that we want to solve a problem about finding a large matching in G. We're good at perfect matchings. We take our problem on this graph G and we make a new graph G plus where solving our problem in G amounts to solving a known problem on G plus. Okay, so one more theorem. This one is due to Peterson. And this is an easy one. It says that if you have a 3 regular graph with no cut edge, then you have a perfect matching. There's an easy fact here about 3 regular graphs. I mean, this actually works for odd degree, but I'll just say 3 regular. The observation is if G is 3 connected, and I give you a subset of vertices of odd, sorry, 3 connected, 3 regular. So 3 regular means all vertices have degree 3. So if I give you a 3 regular graph and I give you a subset of vertices with size of x odd, then the number of edges with exactly one end in x has to be odd. And this is easy. This is a thing we've seen this before in various guises. Here's my set X. What happens when you add up over all vertices in X, the degree? You're counting the number of edges with both ends in X twice, right? This is going to twice the number of edges with both ends in X plus 1 time the number of edges with one end. Oops. right? And so in this case, what's happening? Well, if x is odd, then if x has odd size, capital X is a set of odd size, then I'm adding up an odd number of 3's here. That means this number is going to be odd. Well, twice anything is even, so therefore this third number is going to be odd. So this works the other way around. If I told you the size of x is even, then you'd know the number of edges sticking out is even. So and more generally, this just works anytime you have a graph where all vertices have odd degree. If all vertices of your graph have odd degree, then when I take a set of vertices of odd size, you have an odd number of edges sticking out. When I take a set of vertices of even size, you're going to have an even number of edges sticking out. So that's our key observation here. And what we're going to be looking at in this problem are graphs that are 3 regular, so all vertices have degree 3, and they have no cut edge. So you never see a subset of vertices with exactly one edge sticking out of that to the rest of the graph, because that would be a cut edge. And so if you have a 3 regular graph with no cut edge, then it actually means that for every subset of vertices, of odd size, you're going to have at least 3 edges leaving that set. So let me make that a further observation here. So if G is 3 regular and a no cut edge, and I tell you that x is some subset of vertices with size of x odd, this implies that there are at least 3 edges with one end in x, with exactly one end in x. So that's our key feature. So if you look at a subset of vertices of odd size, it's going to have at least 3 edges sticking out. I've written this sort of weirdly. I'm going to cut this and drag this one up. Save space. Okay, so there's our key observation. You possibly see already how this thing is going to get used. So our theorem here, which is originally due to Peterson, is if G is 3 regular and has no cut edge, then it has a perfect matching. So let's prove. So we're just going to check that Tutte's condition holds. And this is really quite straightforward. So we're going to let X be any subset of vertices. And I'll let, let's say G1 up to GT be the odd components of G minus X. Okay, and so I'll draw our picture again as usual. So there's X. So here's G1, and here's G2, on down to GT. Maybe there's some even components. Won't worry about them. And now what I'm wanting to do is what? I'm trying to prove that you've got fewer odd components than the size of the set X, right? If we can prove that for this arbitrary subset of vertices X, the number of odd components of G delete X is less than or equal to the size of X, then we're done. Then Tutte's theorem will tell us that we're guaranteed a perfect matching. So that's what we'll try to show. And so what I want to get a handle on here is how many odd components we have versus the size of X itself. But what we're seeing here is a nice little bipartite graph, right? There's a nice little kind of bipartite graph here in between, right? So the let's let let's let S equal the set of edges with one end in X and one end in some G sub I. So this is our set of edges S. And now the key thing here is what? Well, so I think in the note, actually, I don't even remember exactly how I did this in the notes. I mean, I'm doing the same argument. There's the same argument every time. There's a little matter of how you state this. There's just some terminology questions, but we basically have a bipartite graph here. I can ignore the even components. You can imagine taking each of those odd components and identifying it to a vertex and just looking at this little bipartite graph. So ignore any edges that have both ends in X and look at this little bipartite graph between the GIs and the X's. And what we're going to see there is that, well, every vertex in X, it's a vertex of the original graph. Its degree is at most 3. I mean, that vertex in X might have had some edges that go to some even components or to somewhere else in X, but the number of the number of edges of S incident with that vertex in X is going to be less than or equal to 3. On the other hand, each of those G sub I components, by our observation above, it's going to have to be incident with at least 3 edges in S. And what that means is that we can, we're going to get a bound. So in fact, let me go ahead and draw the little bipartite graph since I've said it. So S is a set of edges with one end in X, one end in some G sub I. I'm just going to draw it. I'm going to form a bipartite graph. Maybe I'm not going to write all of it, but I'm going to form a bipartite graph where I make each of these a vertex. So here's my bipartite graph H. Hopefully it's clear what I'm doing. So again, I'm deleting the even components from the graph. I'm deleting any edge with both ends in X. For each of these G sub I components, I'm just identifying it to a vertex. If there are edges with both ends in that set G sub I, they sort of form loops or something, but just throw them out. So I'm just left with this bipartite graph H. S is now the edge set of H. And now I can play this game where I sum up the degrees of the vertices on the left, and I count the number of edges in S, and I can sum up the degrees on the number on the right, and I count the same. So the size of this set S here, this is going to be the sum as I runs from 1 up to T of the degree in this graph H of this G sub I. This is also equal to the sum over all vertices X and X of the degree in the graph H of X, right? If I give you a bipartite graph, the number of edges in that bipartite graph, I can get it by either summing the vertex degrees on the left-hand side or on the right. Now, now what's happening again, because of our observation, we know that each of those G sub I components has at least 3 edges. So that means this quantity here, over here on the right-hand side of my equation, well, each of those degree of G sub I's, that's less than or equal to 3. So this is less than or equal to 3T. On the other hand, let me switch this over. On the other hand, these degrees of my X vertices in H, again, those vertices in X, they're vertices in my original graph G. In G, they have degree 3 because I have a 3 regular graph. What's happening in H? Well, their degree can go down, but it certainly can't go up. So that means that the degrees of the vertices, the degree in H of each of these vertices X and X is going to be less than or equal to 3. Oh, sorry, I got this. My apologies. I got this inequality backwards. Again, each GI, each gi is going to have degree, its degree is going to be greater than or equal to 3. So I get greater than or equal to 3t over here on the right-hand side. On the left, the degree in the graph h of x is going to be less than or equal to 3. So on the left-hand side, I get that 3x is greater than this degree sum. And so I have size of x is greater than or equal to t. And so what I'm learning is that the size of x is going to be greater than or equal to the number of odd components of g minus x. And again, x was arbitrary. X was an arbitrary subset of vertices. Because x is an arbitrary subset of vertices, this holds true every time. And then Tutte's theorem tells us we have a perfect matching. So, so 3 regular graphs that don't have a cut edge will always have a perfect matching. That's a pretty theorem due to Peterson. But now we have this kind of powerful hammer of Tutte's theorem, and it's actually very easy to prove. This isn't Peterson's original proof. Okay, so that's going to do it for this lecture. That was a couple of corollaries of Tutte's theorem, and that'll be that.